Hey everyone, and welcome. Today we are diving into one of the absolute most powerful tools in all of physics. It's called the free body diagram, and it's basically a simple sketch that lets us see a whole world of invisible forces at play all around us.
I mean, really think about it for a second. That chair you're sitting in, the phone in your hand, even a satellite whizzing around the Earth, they're all caught in this constant, invisible tug of war. So how in the world could we even begin to map all of that out?
Well, it turns out there's this beautifully simple type of drawing that just pulls back the curtain on all of it. It reveals the complete story of all the forces acting on any single object you can think of. And yeah, you guessed it, it's called a free body diagram.
Okay, let's get into what these things really are. The best way to think of a free body diagram, or FBD for short, is as a kind of force map. Its whole job is to take one object, and just one, isolate it from everything around it, and show us exactly what's pushing or pulling on it.
So here's the official textbook definition. But let's break that down. It's a special kind of drawing that uses arrows to represent forces. And the two most important words there are magnitude and direction. Basically, how long the arrow is tells you how strong the force is, and whichever way it's pointing, well, that tells you its direction. Simple as that.
And this is a perfect example of what I'm talking about. We take the object, in this case, a book, and we just simplify it into a box or a dot. Then, the arrows pointing away from it, those are all the forces acting on that book. It's clean, it's simple, and it tells you the whole story in a single glance.
Now, to draw these force maps right, you've got to know the cast of characters. You know, the most common forces you're going to run into out there. So let's meet the key players.
First up, you've got gravity. That's Earth's constant downward pull. Then you have the normal force, which is just a fancy way of saying a surface pushing back. Tension is any pull from a rope or a string. And of course, we have friction and air resistance, those two troublemakers that always try to oppose motion. Honestly, knowing just these five will get you through most everyday physics problems.
I know, this might seem a little complicated at first, but don't worry. There is a super straightforward four-step method you can use every single time to draw a perfect free body diagram. Let's break it down.
Okay, step one, and this is the most critical part. You have to identify all the forces acting on the object. Just ask yourself, is gravity pulling on it? Is it touching anything? Is there a rope attached? Step two is easy. Figure out which way each force is pointing. Step three, simplify your object into a dot or a box. And finally, step four, draw and label an arrow for every single force. And remember, stronger forces get longer arrows.
All right, that's enough theory. The absolute best way to really get this is to just see it in action. So let's take our four-step method and apply it to a couple of classic examples.
So here is our first case. We've got a book, and it's just sitting still on a tabletop. It really doesn't get much simpler than this, which makes it the absolute perfect place for us to start.
So, I want you to take a second and actually think through our four steps. What forces are really at play here? And which directions are they acting in?
You got it. There are just two forces here. The force of gravity, which is pulling the book down, and the normal force from the table, which is pushing right back up. Now look closely at the arrow length. Because the book isn't moving, it's not flying up or crashing down, those forces are perfectly balanced. That means the arrows have to be the exact same length.
Okay, let's kick it up a notch. For our next example, the book is now being pushed, and it's actually speeding up. It's accelerating, and this one little change, well, it changes everything.
So, check this out. On the left is a book moving at a steady, constant speed. The push to the right is exactly equal to the friction on the left. The forces are balanced. But on the right, where our book is accelerating, that means the forces are now unbalanced. See how the applied force arrow is longer than the friction arrow? That creates a net force to the right, and that's what causes the book to speed up. That visual difference in arrow length, that is the entire story of motion, right there in one picture.
Now that you've got the basics down, I want to share a little pro tip with you. This will help you avoid the single most common mistake that people make when they're first drawing these diagrams.
And it really comes down to this. As one expert puts it, clarity is everything. You have to be absolutely 100% crystal clear about which object you are analyzing. This is where everyone gets tripped up.
So here's the golden rule. Your diagram must only show the forces acting on your chosen object. Do not, and I mean under any circumstances, include forces that your object is pushing or pulling on other things. So for the book on the table, you draw the table pushing up on the book. You do not draw the book pushing down on the table. That's a whole different force story.
So, the biggest takeaway here is this. Just remember the name free body diagram. You have freed the body from everything else around it, so you can tell its story and its story alone.
So next time you see something, literally anything at all, doesn't matter if it's moving or perfectly still, just take a second. Try to picture that simple little box with the arrows pointing out from it. Can you start to see it? Can you see that invisible force story that's playing out everywhere, all the time?